Hello, fabulous assisting students. Here we are for the second podcast, and this podcast is on the physics and characteristics of radiation. Excellent podcast for us to be creating because this is tough information. You guys seem like you did a fabulous job understanding this in class. You were either just trying to make me happy by nodding and smiling and making it seem like you were understanding, or you really did understand, which I think is what you did. So excellent job. And hopefully listening to this again will reinforce and reiterate what we're talking about here with the physics and characteristics of radiation. Week 5. So let's start with the EMR spectrum. What we mean by spectrum is just a variation in types of radiation. So the EMR spectrum is all of the kinds of radiation that there are. The first two that we need to talk about are the two that are potentially harmful, and those are gamma rays and ultraviolet rays. Two that we really need to pay most attention to. Gamma rays being X-rays and ultraviolet rays being rays from the sun. The reason why these two are harmful is because they're capable of ionization, and we need to make sure that we understand what we mean by ionization. So what is an ion? If you look at page 11 in your textbook, you'll see at the very top of the page a molecule of water. And a molecule of water consists of 2 hydrogen atoms and 1 oxygen atom. They're connected by the little negative sign between them that are connecting them together. Those are electrons. So if we go to the figure 2.6 below it, it's showing even an easier example here of one atom that has 2 protons in the very center of the atom, and protons are positively charged. So that is the little pluses in the middle of the circle there. That's the nucleus of the atom. There are 2 protons. The 2 other little circles in the middle of the atom there are neutrons, and neutrons are neutral. They have no energy whatsoever. And then electrons are the negatively charged particle that orbits the outside of the atom. So we have 3 parts to an atom that we need to know. Actually 2 parts. The electron, which orbits the outside, and the proton, which is on the inside of the atom. And they need to be equally balanced. Same amount of protons to electrons. As long as we have the same amount, it's balanced and there is no energy. Where we get energy is when we have an electron either added or taken away from the atom, so there's an imbalance or more protons or electrons. So the analogy that I used in class was I took Mandy's hand and we pulled with equal force. So her force equaled my force and we went nowhere. No energy. So if we have the same force of the protons with the force of the electrons on the outside, positive and negative force being the same, there's no energy. Where we get the energy is when there's an imbalance, so we either add or remove electrons. If you look at the bottom of the page 11 there on the left-hand side, ionization, atoms can exist in a neutral state or in an electrically unbalanced state. Normally, most atoms are neutral. A neutral atom contains an equal number of protons, positive charges, and electrons, negative charges. An atom with an incompletely filled outer shell is electrically unbalanced and attempts to capture an electron from an adjacent atom. Go down to the last sentence in that paragraph. An atom that gains or loses an electron and becomes electrically unbalanced is known as an ion. Ionization is the production of ions or the process of converting an atom into ions. The 2 types of radiation that we just mentioned, gamma rays and ultraviolet rays, both are types of radiation that are capable of penetrating our tissue and changing our cellular structure inside our bodies to gain or lose electrons. And that imbalance in our cells is what enough of it can cause cancer. It changes our cells, mutates our cells, and we don't want that. So gamma rays and ultraviolet rays are both capable of ionization, which is a bad thing. We don't want that to happen. Other types of radiation include visible light. So as we're sitting in the classroom and light is streaming through the windows, there is radiation from that. Now that radiation is not strong enough to penetrate our tissues. Therefore, it is not harmful. It is not capable of ionization. Infrared is another example from infrared scopes. Radio waves, electric waves, those are both types of radiation that are not potentially harmful. They're not of a nature that is enough strength that could potentially hurt us, and it can't penetrate our tissues. Looking at this slide here, this shows us where visible light is. Visible light, the solid vertical thick line there in the middle, visible light, is where we get all of the colors that we can see, and all the light that we can see is there. Outside of that visible light, we can't see. So radiation is not just visible light, it's not just X-rays, it's not just gamma rays are from the sun, but all different types. So you can see here on the very far left side, we have gamma rays, then X-rays, then ultraviolet light, which is real close to visible light. And Dre asked a good question about ultraviolet light and really trying to understand what it is. And it is a light in the light wave that is outside of the scope of what our eyes can actually see. I did upload 2 videos into the D2L classroom on ultraviolet light. One is really old and hokey, but it's excellent and does a fantastic job of explaining what ultraviolet light is. Then we have infrared, which is on the other side of the red color of the visible light that we can see, so we can't see that either. And then radio waves. On page 13 of your textbook at the very top, you see the same type of thing, just in a different figure. So we can see at the very top there, your wavelength, and we're going to talk about wavelengths here in just a second, but the most harmful types of radiation at the very top and uses would be radiotherapy. So X-rays and gamma rays, certainly X-rays for radiotherapy, gamma rays not so much. Then we have dental radiography, the sun, photographs, microwave, then we have sonar, television, and radio. On the top of page 13, you can see figure 2.8 that shows us the same type of thing, although it is just in a different format. You can see on the left-hand side the energy type, which is X-rays and gamma rays. On the left side there talks about the wavelength, which we're going to talk about in just a second, and then on the right side what the uses are for. So radiotherapy, using radiation to heal our bodies, and it's really not to heal our bodies. Yes, long term is, but what happens with radiation treatment is that we're using that radiation treatment to kill the cancer cells. So we're actually introducing very harmful substances into the body, but that is because that is less harmful than the cancer that's in our body already. So we introduce, or we put in, the radiation into the body that does hurt us, but it's killing the cancer, and hopefully we will recover from the negative effects of the radiation. Then the cancer is dead, will be cancer-free, and then can continue to live a long and prosperous life. Then we have dental radiography, radiation from the sun, photography, microwaves, radar, television, radio waves. So what makes radiation harmful? What actually makes it harmful is the length of the wave. Now, we're not talking about how far it can travel. We're talking about the length there is, or the space between the peaks. Radiation travels in a wave-like format. So if we were to measure between the crests of the waves, the further the crests of the waves are from one another, the less energy there is. It's not very strong. The closer together the wavelengths are, the higher the frequency, the higher the energy, the stronger it is going to be. So not distance that it can travel, because again, let's think of sunlight. Radiation from the sun travels many miles to get to the earth, yet it's still strong enough to penetrate our tissues and give us skin cancer. That is because the length between the crests, as the radiation travels in a wave, they're very, very tight together, and that causes energy that can be harmful to us, penetrate our tissues, and cause ionization. Long waves are not harmful. Short waves are harmful. Okay, so we need to understand the atom in order to understand where we get radiation from, because we have to understand electricity. And in order to understand electricity, electricity at its most basic explanation, we need to understand an atom. So as I've already said, we've got the picture here of an atom with the protons on the inside, the electrons orbiting the outside. Neutrons are neutral, they don't have any energy. And we're going to use these negatively charged particles, the electrons, to create electricity. So then what we did in class was we drew a glass vacuum tube. And the glass vacuum tube is the inside of our X-ray head. That is where the radiation is produced, and it's produced from the use of electrons. So I'm going to use this slide right here, and you'll have to follow along with me either with this slide or with the drawing that you made. I would encourage you to probably use the drawing that you made just to make sure that it's accurate, and that will probably also trigger more memory for you since you drew it yourself. What we have when we turn on the X-ray head is we've just created electricity. So just like flipping on a light in a fraction of a second, and again, remember, radiation travels at approximately 186,000 miles per second. Now, just to clarify or to fix an error in your textbook, if you're looking at page 13, Box 2-1, the third bullet down says travel at the speed of light. Then it says 3 times 186,000 miles per second equals 108 meters per second. That's actually opposite. If you look at the adjacent page 12, almost exactly adjacent to it, where it's talking about velocity, that is correct there, where it's stating that the speed of light is approximately 3 times 108 meters per second, which is 186,000 miles per second. So the numbers in your box 2-1 are opposite. The large number, the 186,000, miles per second switch with 108 meters per second, and then it would be accurate. Anyway, nothing critical to worry about. It travels very, very, very fast. So when we turn on our X-ray unit, and ours are underneath the machine, you flip it on, in that fraction of a second, you've just created ionization. You have pulled ions off of atoms, and they're now sitting on the cathode side, or the right side, the negative side of your glass vacuum tube. They're sitting in there, and they're attracted to a coil in there that attracts the electrons. So as soon as we've turned on the electricity, the electrons are sitting there waiting to be used. They're not being used yet. They're not going to be used until we push the button, but they're waiting. I didn't use this analogy in class, but I have for a long time, of turning on your DVD player. Of course, back in the olden days, I used to say turned on your VHS player, but some of you probably don't even know what a VHS is. So anyway, it is turning on your DVD player. Even though you turned it on, that doesn't mean it's playing. That means the power is on, but we still have to hit play in order to make it work. So same thing here. We've turned on the power to our X-ray head. We've created electricity. We've pulled electrons off of atoms ready to be used. They're clustered on the cathode side of the glass vacuum tube. When you push the button then, so you put the film in the patient's mouth, you go outside, you push the button, you are now releasing the electrons, and the electrons are capable of leaving that cathode. When they leave the cathode, they're going to want to be reattached to the rest of the atom. So the rest of the atom is on the left-hand side there, on the anode side, or the positive side of the X-ray tube. There is a magnetic pull between the cathodes and the anodes, and they want to be together. But if we were to let them to reunite, we would lose the energy. Remember, if we have the equal amount of electrons to protons, then we have zero energy, none. We don't want to lose our energy, so we're not going to let them unite with the anode or the rest of the atoms. We put something in the way, and that something that we put in the way is a metal plate. It's made out of tungsten, which is a type of metal that has a very high melting point. What that means is super, super, super strong. It's the type of metal that a lot of wedding rings are made out of these days. It's become very popular to have them made out of tungsten because then they won't change shape over time. So when you push the button and you release the electrons, they immediately shoot over towards the anode. They cannot reunite with the protons. They hit the metal plate that's made out of tungsten called the tungsten target. And that reaction that happens by the electrons hitting the tungsten target, they bounce off and they create radiation, or properly called photons, photons, photons. So photons are the ray produced from the electrons hitting the tungsten target. Now that ray is directed at our cone, or our PID. It's directed in that direction. We're not ready for that ray, though, to be allowed to come out of the cone, because if we allow the ray to come out of the cone at that point, we are allowing way too much radiation to come out, and it could be harmful. So we need to restrict it. There are two things that we put in the way to restrict it. The first thing we put in the way is an aluminum filter. The aluminum filter, yes, radiation can go through aluminum, but aluminum is a fairly thin sheet of material, and some radiation, the strongest beams of radiation, can go through that aluminum. So whatever can get through that aluminum is certainly going to be strong penetrating beam, and we can use it. All of the weak radiation is going to stay inside the X-ray head and not be released, and it'll just dissipate quickly in the X-ray head. The next thing that we have in the way so that we don't let all of the radiation out is what's called a collimator. It is a lead washer. The lead washer is a ring that does not allow radiation to come out anywhere but from the hole or the portal in the middle of the washer, because lead is the metal that radiation cannot go through. So if you look at page 15, you can see in the bottom of the page, figure 215, you have a lead washer right there, and that lead washer goes in your cone and restricts the beam so that it only comes out of the very middle or center of that cone. If you look at the picture right above it, figure 214, you can see in the X-ray head itself the aluminum filter that's in the head itself, and then the black collimator that is in the end of the cone. Now, the opening for the collimator needs to be a specific size, and the size for that hole needs to be the correct so that when the radiation comes out of that hole and travels down the cone, by the time it hits the very end of the cone and it is spreading out there, it is no wider than 2.75 inches. You absolutely need to remember that number. So the purpose of the collimator is to restrict the width of the primary beam or main beam, the X-ray beam that's aimed at the patient, so that it is only the width of the end of the cone, which is 2.75 inches. Now, of course, if you pull the cone away from the face 6 inches, now the radiation is spread out even further, because the further you pull the cone away from the face, the more spread out the radiation is going to be. So again, the collimator only restricts the width of that radiation beam to the 2.75 inches at the end of the cone, and that's why it's important to have the cone somewhat close to the face, because we don't want it spread out and radiating parts of the body that we don't need it to. The primary beam, again, is aimed at the patient, the teeth and film, and then it doesn't just stop though. Once it hits the teeth and film, it bounces off. The radiation that bounces off is called secondary radiation, and then it bounces around, called scatter radiation, until it loses energy. I use the analogy of throwing a ball against the wall. You throw a ball against a wall, it's not going to just stop once it hits the wall. It's going to bounce back, and it'll keep bouncing around and hit the table and chairs and whatever else until it has no more energy. And that's what radiation does. Again, that happens very, very quickly because radiation travels 186,000 miles per second. So it's going to go fast, 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 fast. There's a fourth type of radiation. So we've talked about the primary beam, the secondary beam, and the scatter radiation. And then there's leakage radiation. Leakage radiation is here on this drawing, right above the center arrow illustrating where the portal is the radiation that could come out if your cone is not twisted tightly onto the X-ray head. If the cone is not twisted tightly, then radiation can leak out, and that's the fourth beam or fourth type of beam is probably the best thing to remember, the fourth beam of radiation. Of course, make sure you know that the cone is properly called PID, which stands for Position Indicator Device. So that's how radiation is produced. Inside the X-ray tube, it's made out of glass. There's a negative side, a positive side. Negative side is cathode. Positive side is the anode. The electrons are released, hit the tungsten target, aimed towards the cone, goes through the aluminum filter, then through the center of the lead collimator or lead washer, which is a collimator, and then out down the cone, restricted to the width of the end of the cone to 2.75 inches. Looking at your textbook, if you look at page 14, you can see there's a description of the tube head there. There's the aluminum, it says aluminum disc, but that's the same thing as the aluminum filter. On the next page, 15, talks about the lead collimator, and then the PID, the position indicator device. Talks about the cathode and the anode on the next page. There's another diagram of the inside of the tube head at the bottom of page 16. Also talks about the tungsten target in the middle of the page there. Don't worry about the copper stem. We're good. We've covered everything you need to know. Here again is the drawing. This slide illustrates again the radiation beams. You have the primary beam aimed at the patient, also called the main or central ray, aimed at the patient. Secondary and scatter is what bounces off and bounces around for a while. And then leakage can come from a cone that's not on tightly. Make sure you know the two of those four that could be harmful to you as the operator would be scatter and secondary radiation, because that potentially can travel 6 feet. So if you're standing close within 6 feet of the patient, or 6 feet of their head, you would be within the area where secondary and scatter radiation can travel, and that could hurt you. The primary beam's not going to hurt you because it's going to be aimed at the patient, and leakage radiation is not going to be strong enough to hurt anybody. It just kind of seeps out a cone that might not be on tightly. Okay, now we need to understand KVPs and MAs. They're described for you on page 17 of your textbook. And KVPs and MAs have to do with the electrons that we've already talked about in the tube head. It's talking about the speed of the electrons and how many electrons are released. So when we release the electrons from the cathode in the tube head in order to create radiation, if we only release one and release it very, very slowly, we're not going to produce radiation. There's a certain amount that needs to be released and at a certain speed. KVPs is the speed of the electrons moving from the cathode to the anode. So how fast they are going. If you have KVPs set very low, that's going to give you high contrast. What that means is that there's a lot of difference between black and white. So looking at this chicken wing here in this picture, the one on the right-hand side has high contrast. You can really see a big difference between the black and white, and not a whole lot of shades of gray. So that's high contrast. That means you had the KVP setting very low. That is good for diagnosing decay and periapical abscesses. This slide says just abscesses, but I would add the word periapical abscesses, which are in the bone. You could also see fractured bones and that kind of thing very well with high contrast. Now what we're going to see really well with low contrast, the picture on the left, is not the hard bone structure, but is the soft tissue around the bone. We have low contrast. There's a lot of shades of gray there. We're going to do a lot better job looking at it in low contrast of diagnosing periodontal disease and periodontal abscesses. This slide again incorrect should say periodontal abscesses there at the bottom. So change that last word at the bottom of the page there. It says periapical abscess. That should be a periodontal. Again, the difference. Periapical abscess is an abscess in the bone at the tip of the root of the tooth, and periodontal abscess is an abscess in soft tissue. So if we want high contrast, we're going to set our KVPs low. If we want low contrast, we're going to set our KVPs high. So if you look at this question here, which one is higher contrast? Which one can we see a big difference between black and white? Well, that would be the one on the right-hand side. High contrast, that means it was low KVPs. B has more contrast, more black, white, and shades of gray. In this picture, which one has higher KVPs? If we have higher KVPs, it's going to give us low contrast, so it'll be the one on the left. More KVPs gives us less contrast, so more shades of gray. The one on the right, we're going to be able to diagnose decay and periapical abscesses. The one on the left, we're going to be able to diagnose periodontal disease and periodontal abscesses. KVPs are the setting The speed is what we want to control, the speed of the KVPs, in order to give us good quality. So the quality of your x-rays are controlled by your KVPs. MAs refers to the amount of electrons, how many electrons are released from the cathode to the anode. Easiest way to remember this is the A in amount in MA stands for amount, controls the number of electrons. And that says controls the number of x-rays. That should probably more correctly be controls the number of electrons. When milliamperage is increased, exposure time must be decreased. If we increase the numbers of electrons, the more electrons we release, that means the image is going to be darker. The darker the image is going to be, the less exposure time we want. So that's a good thing. We actually want high MAs so we can decrease our exposure time and the patient will get less radiation in time, although the radiation is then stronger. That's kind of a wash, maybe. If you're looking at page 17 of your textbook, left column, a little bit higher than the middle of the page, amperage is the measurement of the number or amount of electrons moving through the conductor. Current is measured in amperes or milliamperes. Voltage is the measurement of electrical force that causes electrons to move from a negative pole to a positive one. Voltage is measured in volts or kilovolts, kVs, and again, that's the speed. In the production of x-rays, both the amperage and the voltage can be adjusted. In the x-ray tube, the amperage or number of electrons passes through the cathode filament can be increased or decreased by the milliamperage adjustment on the control panel. So yes, you can adjust the MAs and KVPs, although you probably will never do so. We never do so in our units. That's not something that you typically will adjust. Now, in the olden days, yes, we used to adjust those controls to get a better picture, but x-ray control panels now are so calibrated that it is best left to your technician that is responsible for calibrating your x-ray head. They will set it to what is best, and you will probably never adjust the MAs and KVPs. When you adjust something on your x-ray head in the x-ray lab, what you're adjusting is the exposure time, not the MAs and KVPs. For film, we need more time exposure. We increase the time for conventional film and decrease the time for the digital sensor. The control panel has a master switch. That's just your on and off, easy. Has a timer switch. Now, we didn't get a chance to talk about this in class. Basically, what that means is you're setting the time on the control panel, but when you push the button, it has to have an automatic cutoff. So you can push the button to take the x-ray and to create radiation, but you could stand there and push the button for an hour and it will have cut off 59 minutes and 30 seconds ago, and you're not emitting any more radiation. In the olden days, x-ray heads, and I never worked on one, but x-ray heads used to not have an automatic cutoff switch. So you would have to push the button for the right amount of time and release it at the right amount of time in order to stop the radiation. They can't make them that way anymore. It's a regulation that they have to have an automatic cutoff switch. So you're not in control of how much radiation or the exposure time via pushing the button. Yes, you're in control because you can change the setting, but you are not in control at the time that you're pushing the button, because that would just be easy to have variables. One time you'll push it for 5 seconds, the next time you'll push it for 20, the next time you'll be talking to someone and forget you're pushing the button, you just radiated your patient for 5 minutes. Okay, and then you have milliamperes, which is the amount of electrons, and KVPs, which is the speed. If you look at the bottom right column of this slide here, it tells you the common settings, whether or not you have a short cone or a long cone. When we have a long cone, the radiation has to travel a further distance. So to give us the same quality x-ray, you would need to increase the amount of electrons and the speed of your electrons to give you the same quality x-ray. They're traveling further. A short cone, you wouldn't need the same amount or speed because they're not traveling as far. So notice that the numbers for short cone is 10 MAs, and 70 KVPs. For long cone is 15 and 90. And those are approximate. They're common settings. I think you'll notice with our x-ray heads, it's set at 15 and 70. not 10 and 70. So those are approximate numbers. Just know the concept that long cone, you would have to increase the milliamperes and the kVps because the radiation is going to have to travel further. A couple more terms we need to know. One is density, and density, there are two different ways we use that term. The first way we use that term is in reference to the density of the film. That means comparing one film with another. When you are comparing one X-ray to another, one that is darker, overall, it's darker or blacker, it has more density. It looks, I just came up with a good analogy. If you're looking in a swimming pool, and in the swimming pool, the water is very, very clear, and you can see a long distance in the water, it's not very dense. It's clear. But if it's all muddied up and it's dark and you cannot see in it very well, that's dense. Darkness is dense. Now, the other way we talk about density in relation to X-ray is the density of an object. The thicker an object is, like in this picture here where we have a crown on the tooth and a post and a root canal, the thicker an object is, the radiation cannot go through it. So the thicker it is or more dense the object is, radiation cannot go through it, and that's going to appear whiter, more white in color. Notice where it says radiolucent, that is a dark shadow at the apex of the tooth. That is radiolucent shadow, is because the bone is being eaten away in that area by the infectious material in the tooth. There is no bone there, no density, and so it shows radiolucent. So remember, when we talk about density, you have to know if we're talking about density of the film, the overall darkness of the film, or if we're talking about density of an object, which would then end up showing white on your X-ray. In your textbook on chapter 2 that we've been looking at, in your homework is going to go over what Compton X-ray is, these pictures on page 20 and 21. Find the right answer for your homework, but don't memorize. Don't waste brain cells trying to memorize and understand that. Is it the photoelectric effect? Is it a coherent scatter? Is it a Compton scatter? No stress about really understanding that. Find the right answers in your textbook, get the right answers for your homework, and then forget about it. That's not critical. Let's look at page 79, and again, we didn't get a chance to talk about this in class either. Page 77, chapter 8, and let's go back to page 77. Chapter 8 of your textbook is another chapter that we're going over this week, and it has these terms that we've already talked about here. Radiolucent means something that is going to show up dark on the X-ray because the object is thin. Air spaces are going to show up black on the X-ray because it's thin. There's no density there. Radiopaque means white, and that would be what shows up on an X-ray behind something that is thick or dense. We've already talked about that a lot. Density is described there on the right-hand side of page 77. Again, there's two different characteristics, density and contrast. Contrast, and let's talk about it with the slide here. Contrast means that we're comparing. When you're contrasting things, you're comparing one against the other. On an X-ray, if we say that it has high contrast, that means there's a big difference between black and white. And we've already talked about that in reference to our kVp setting. The higher the contrast is going to show very dark areas and very light areas. The lower the contrast is going to give us shades of gray. Look on page 79. You've got 3 pictures there of basically the same thing. They're not exactly the same picture, but probably taken one after the other with some changes. If you look at the figure A at the figure 8.4a, which is the top picture, that is high contrast. You can see a big difference between the black and the white. That would be low kVps. The one in the middle is actually the best quality or the best settings, which is medium contrast. Really medium. High and low contrast are both, neither are good. We don't want too much contrast or too little. We want it kind of in the middle to give us a good contrast to be able to see everything on the X-ray. Now again, I think I mentioned in class that our new digital sensor has settings where you can change the settings of a picture to be able to see it in higher contrast or lower contrast depending on if we're looking for soft tissue disease or hard tissue disease. If we're looking for hard tissue disease, we want high contrast, so that would be lower kVps when you're taking the X-ray. If you are looking for periodontal tissues, that would be low contrast, more shades of gray, which when we take the x-ray would mean it would be higher contrast, or higher KVP, higher KVPs. On page 80, talks about the step wedge, which we've already talked about, so you should know what that is. I did mention the word penumbra. There's a description of it on the bottom left of page 80. Penumbra can be defined as the unsharpened or blurring of the edges of a radiographic image. So areas on an x-ray that aren't real clean and clear and crisp that give us a good picture of what's going on is called penumbra. Above that, right underneath where it says geometric characteristics, are some other terms. Sharpness. That's pretty obvious what sharpness is, also known as detail or resolution, where you can make out different things very easily. Magnification, which means making it bigger, and we know that the further we take our film away from the tooth in the mouth, so not putting the film right up against the tooth as you have it in the middle of the mouth for paralleling technique, is going to cause image magnification. It's going to cause the image on the x-ray to be a little bigger than it really is, and also cause a little distortion. Distortion means it's not exactly looking like how it is in real life. It's distorted. On the bottom page 81, the very first paragraph talks about the smaller the focal spot area, the sharper the image appears. The larger the focal spot area, the greater is the loss of image sharpness. I have a note here that is a test question, although I don't remember it being one, but somebody must have come back from the national boards last year saying that was a test question. Basically, what it's talking about with focal spot is the size of the tungsten target. The tungsten target is the focal spot. So the smaller the tungsten target, the less penumbra you're going to have, or the less artifact. Look at the picture on the very top of page 81, figure 8.7. You can see where we have the anode and the tungsten target there. They're calling it the focal spot. With a large focal spot, it's going to give you more fuzziness, shadowing, so you're going to have more penumbra, where the smaller the focal spot is, the less extra artifacts you're going to have. The smaller the penumbra, the less like shadowing in the back, and it looks pretty obvious there on that figure 8.7. On the top of page 85, hopefully this will help you on your homework. Figure 8.16, above it I would write on there, above the B, the middle of figure 8.16, that would be, hopefully you know, is it high, medium, or low contrast? That's actually high contrast. There's a big difference between the black, white, and the little bit of gray in the middle. I'm not sure why I have it listed here this way, and I'd have to look at the questions, but what I have on A is low contrast. I don't know that that's really low contrast. That would be medium. If I'm saying high, medium, and low, I would say B is high contrast, A is medium contrast in the middle, and C is not low contrast, it's no contrast. There's zero contrast because there's only gray. There's nothing to compare it with. There's no contrast. So I have A listed as low contrast, B as high contrast, and C as no contrast. Hopefully that'll help you and not confuse you with your homework questions. Okay, let's go over and make sure we know what all of these terms are here. Aluminum filter is the filter inside the X-ray head that keeps the weak radiation inside the X-ray head, only allowing the strongest radiation to come out. A milliampere is an amount of electrons. Milliamperes are the amount of electrons that are released or used to create radiation. The anode is the positive side in the X-ray head. An atom is a small element, tiny element that has protons and electrons, and everything in the earth is made out of atoms. There's different amounts of molecules and different types of molecules with the making up different substances. So an atom has protons and electrons. The cathode is the negative side of the glass vacuum tube. The collimator is the lead washer that restricts the size of the beam, primary beam, to 2.75 inches at the end of the cone. Cumulative means, we didn't talk about that. Cumulative means that radiation adds up onto itself. So the concept here is that when we get radiated, we have that radiation in our body. And I used to say, until I got smarter, I used to say that radiation there was no way to get radiation out of your body. That really isn't true. Our body is so amazing, as we talked about in anatomy, that your body actually can heal itself of the harmful effects of radiation. Now, obviously, that would depend on the amount of radiation you've received and the amount of damage that has been done. But radiation is cumulative. And that's the reason why we want to limit the amount of radiation that we have, the frequency of the radiation that we get. We only want to take an FMX every 3 years because radiation is cumulative. It'll add on, and the effects will keep adding on the more we take X-rays. Again, over time, your body can heal itself from the harmful effects of radiation as long as it's not too much. It's kind of like laying out in the sun. I think a lot of us like to lay out in the sun in the summer, especially if we're poolside, but we are getting some harmful effects of the sun. That is cumulative, but over time, our body is going to typically heal itself from that harmful effect. And if it doesn't, then we get skin cancer. Density, again, is referring to two different things. Density of the film or density of an object. If we're talking about density of the film, it's the darkness or blackness on a film. If we're talking about density of an object, that's the thickness of an object, and that'll show up white on an X-ray. Distortion means it doesn't look like it really does, so it looks different on the X-ray than in real life. It's distorted, it's different. Electrons are the negatively charged particle of an atom, and that's what creates electricity and creates radiation. EMR stands for electromagnetic radiation. Kilovolt is the speed of the electrons. A kilovolt is a speed of the electrons. An ion is an atom that has imbalance in the protons and the electrons, either has gained or lost electrons. Penumbra is fuzziness on an X-ray, where it is not very sharp or clear or crisp. Photons is the proper term for radiation, as it is created from the electrons hitting the tungsten target. The PID is a position indicator device, proper name for the cone. The portal is the hole where radiation can go through the middle of the collimator. Protons are the positively charged particle of an atom. A Röntgen, remember Wilhelm Conrad Röntgen is the guy who discovered radiation. A lot of times we talk about, or actually we don't, I'm lying. They used to, many years ago, talk about radiation in terms of a Röntgen. You know how doctors are. They want their name forever immortalized in history, so they put their last name on a lot of things. It's kind of like your instruments, a Hollenbach, a Cleoid, all of those. Okay, maybe not all of them, but most of them, if you go back in time and look at where they got their names, it was the last name of the doctor who created it. Spectrum just means types, and tungsten target is the metal that the electrons hit. It's attached to the anode, and that it creates our radiation. Now I am completely exhausted and tired of talking, and you're probably tired of hearing me. So sorry. You know what you could do is when you're listening to me, you could turn up the speed of the voice, and then I would sound like a chipmunk and wouldn't be as obnoxious. There you go. Or more. My son just said or more. Anyway, here we are. We're all done. Nighty night. See you later.